Welcome back, everyone. Today, we're diving right into Lecture 31 by Skip Uni, and we're taking on an absolute beast of a topic, pointers in C++. If you've been scouring the web for a clear, no-nonsense C++ pointer tutorial, well, you're in exactly the right place. Our main goal today is all about truly understanding pointers in C++ by breaking down step by step exactly how a memory address in C++ actually works under the hood. By the time we wrap up this explainer, you're going to have completely mastered both the address of and dereference operators. So let's just jump right in.
Here's a quick look at how our memory journey is going to unfold today. 1. Intro to C++ pointers. 2. What exactly is a pointer? 3. Memory representation. 4. The toolkit, meaning the ampersand and asterisk. And finally, 5. The pointer challenge.
All right, Section 1. Intro to C++ pointers.
You know, if you study computer science, you've probably heard that pointers are one of the most heavily tested, but honestly most feared topics in programming. In modern languages like Java and Python, memory management is totally hidden behind the scenes, right? The concept of pointers doesn't even exist for the everyday programmer. But C++, well, it's a fundamentally different beast. C++ actually hands you the keys to the kingdom. It gives you direct, raw access to your computer's memory. And this incredible power is exactly why this topic is practically guaranteed to show up in your university exams and technical coding interviews.
Moving on to Section 2. What exactly is a pointer?
Whenever students are asked what a pointer is in an interview, they usually give a kind of vague answer like, oh, it references something. But let's redefine this with a bit more precision. Fundamentally, a pointer is simply a variable. That's the best, most accurate way to start building your mental model. However, it's a very specialized variable. Unlike your standard variables that comfortably hold everyday data, like a person's age, a price, or a name, a pointer strictly stores the memory address of another variable. So the absolute crucial takeaway here is this. If you try to stuff a normal integer, like the number 30, into a pointer, your compiler is going to throw a massive error. It demands a memory address and literally nothing else.
Okay, Section 3. Memory representation.
To really wrap our heads around what a memory address actually is, we need to look under the hood. We need to see how your standard lines of code translate into physical storage blocks in a computer's memory. Step 1, imagine you write a super simple line of code, int a equals 10. What physically happens? The operating system allocates a physical memory block, usually taking up 4 bytes of space for an integer. Step 2, it takes your value, the number 10, and securely locks it inside that allocated box. But step 3 is where the pointer magic actually begins. That physical block gets assigned a specific, permanent location in your main memory. Computers represent these memory addresses in hexadecimal format, which you can usually spot by a 0x prefix. So, just for the sake of our explainer today, let's say this specific block gets assigned the hexadecimal address 0x100.
Next up, Section 4. The toolkit.
So now that we know these physical hexadecimal addresses exist under the hood, we need specific tools to extract them, store them, and manipulate them. Our very first tool is the address of operator, represented by the ampersand symbol. Now you might recognize the ampersand from bitwise operations, but here it serves a totally different purpose. Think of the address of operator as your built-in GPS locator. When you place an ampersand directly in front of the variable a, you are basically commanding the compiler to completely ignore that value 10 sitting inside the box. Instead, you're grabbing the physical memory location itself. It bypasses the contents and fetches the address, which in our running example is 100.
Okay, so we've successfully extracted the address 100, but how do we securely hold on to it? Well, we declare a pointer using the asterisk symbol. By writing int star p equals ampersand a, you're basically telling the compiler, hey, create a special pointer variable named p and let it securely hold that fetched address, 100. So now, variable p is officially pointing to variable a.
But hey, before we go any further, you really need to remember this golden rule of pointers. You must match your data types. Seriously, if your original variable a is an integer, your pointer p absolutely must be declared as an integer pointer. If you're pointing to a character variable, you need a character pointer. Why is this so strict? Because mismatched types will cause some really serious, hard-to-track mathematical errors later on when you start doing pointer arithmetic. Keep your data types identical, and your code will stay perfectly stable.
Let's decode how very similar syntax can output completely different results. Looking at this breakdown, in the first row, simply calling a outputs 10. Nothing new there, right? The second row, calling ampersand a, uses our GPS locator to fetch the address, outputting 100. The third row simply calls p, and since p is our pointer that's holding that exact address, it also outputs 100.
It's just absolutely vital to see the distinction in what you're actually asking the compiler to retrieve here. And that brings us right to our second major tool, the dereference operator. Using the exact same asterisk symbol but in a totally different context, like *p, acts almost like a key to a safe. It tells the compiler to go inside. You're essentially giving the command, take the address 100 that pointer p is holding, unlock that specific memory door, walk inside and grab the actual value stored there. By dereferencing the pointer, the output safely bypasses the address and retrieves our 10.
Now here's the practical, real-world application of dereferencing in action. Writing int c equals *p actively uses the dereference operator to safely extract the 10 from that physical memory location and seamlessly assigns it to a completely new, separate integer variable called c. This really just proves how easy and honestly how powerful it is to pull data directly out of raw memory and pass it around your program.
But wait, there's one final twist to consider here. What happens if we run the code &p? The output isn't 100, and it definitely isn't 10. It's 200. But why? Well, because p, despite being a fancy special pointer, is technically still a variable itself. And because it's a variable, it requires its own unique physical space in the computer's memory to exist. So, when we use the address of operator on the pointer itself, we get a brand new memory location, like 200.
Finally, Section 5, the Pointer Challenge. Congratulations on grasping the foundation of pointers. Now, it's time to test your newly built mental model. I'm going to leave you with this little cliffhanger about pointer arithmetic. If you have an integer variable x equal to 15 and a pointer p is perfectly holding its exact memory address, what will be the exact output if you run the code p+1? Think carefully about what pointers actually hold. Remember our golden rule about data types, and think about what adding 1 might logically do to an address under the hood. I highly encourage you to drop your best guess and your logic in the comments. It's a fantastic exercise, and it'll perfectly spark your curiosity for our next explainer. Keep learning, stay focused, and I'll see you next time.